Last day, I talked about how to find the mass of an object with variable density, and that was our goal. But that was only part of the goal. Our big goal is to actually locate the center of mass, or center of balance, or center of gravity. Those are all the same things. The idea is, if I have a three-dimensional object, knowing where the center of balance is has everything to do with things like balance and a car not tipping over when it goes around a corner, or different things. In Calculus 3, you're going to do the same problem, but in 3 dimensions. So you're going to do a much more complete version of this. We're just going to get an introduction today, but we can only look at 2-dimensional things. Next semester, we're going to look at the big picture. It turns out this particular topic is considered one of the more important calculus applications for any engineer. To be able to design something that is stable, whether it be constructing a building, whether it's building an automobile, whether it's simply designing the desk that you sit in. I want to be able to have something that doesn't easily tip over, let's say, that's very balanced and very stable. So the ability to figure out where that center of balance is very important, because if it's located in a place that is not convenient or maybe not even safe, I may have to change the design. So let's go back to high school geometry for a moment. If I gave you a simple shape like a square, pretend this is a square, just a square. This is a massless object. This is just 4 line segments connected. Does this shape have a center of balance? Yes, of course it does. And that is called the centroid. That sounds like a made-up word. The center of balance, center of mass, center of gravity, and an older term is called a barycenter. That is basically what the centroid is. Now, if it's a massless shape like this is just a picture of a shape, the geometric center and the center of balance are going to be the exact same place. And the easiest way to find it in a shape like this, of course, would just be to draw the diagonals and where they intersect. If I took the perpendicular bisectors of each of the sides, they would also intersect there. This point right here, kind of located dead center, would be the centroid. That doesn't require calculus or any calculation. Well, as it turns out, all polygons have centroids that are relatively simple to find if there's not too many shapes. For example, a triangle, finding the centroid, again, if you remember from your high school geometry, if I just take a random triangle, excuse me, the centroid of this shape here was located, if I take the 3 medians, that would be the midpoint to other vertex. That would be the centroid of this shape. Very easy to find in many, many geometric shapes. Now, if my shape is just say a random quadrilateral, it's a little bit harder. I may actually have to use some calculus, but it still won't be very hard. Again, a massless object, centroid's fairly simple. Now, one of the questions that people ask, and it's a good question, does the centroid have to be located any particular place in the object? Well, let's take a piece of paper. Well, actually, I have a box of tissues here, okay? Now, the centroid of this box of tissues is probably located inside the tissues. And there will be a balance point somewhere in the middle here, but this is a 3-dimensional object. So this isn't the one I want to study. The one I want to study would be, imagine now I have simply a 2-dimensional piece of paper. Is there a place that I can put my finger that it will balance? You see, this is not massless. This actually does have mass. Unlike my picture that I had was just 4 line segments, this has everything in between. This is the kind of shape we want to discuss. So is there a place on here, probably the intersection of the diagonals? Yes, because this has uniform mass. The density throughout here does not change in any way. So that geometric center, like crisscrossing, finding it, still works. So the question is, what if the density changed? Maybe it increased from left to right. Maybe it decreased from left to right. Maybe every point on here has a different density. Then finding the center of balance of this thing would actually be quite a bit more complicated, and again, would absolutely require calculus, okay? So with that being said, if I want to locate that center of balance, that center of gravity, we have to start somewhere. And what I want to do, first of all, we did this example the other day. I said, imagine I have a bunch of mass points. And they're located at the x coordinates x1, x2, x3, and eventually xn. I have n distinct mass points with nothing between them. This would be kind of like saying I have people in a row, they're sitting in a desk, but between desks, there's nothing. There's just air. There's just empty space. I would like to know, where can I put my finger to balance all of these things? Now, that's not a trivial question. That's actually a little bit complicated at first. So I'm going to take you to the simplest example that most of you are aware of. Okay?
Still use electro.
Make sure you're muted. You're going to take over the screen otherwise. So imagine this is something you're all kind of familiar with. Hey guys, again, make sure you're muted. Tommy, I think that's you. Your face and your name keep coming up on my screen.
Oh,
okay.
That's so mean.
There we go. Okay. Teeter-totter. Okay, everybody familiar with the teeter-totter? Now, this is placed directly in the center, and let's say these two human beings have equal mass. Okay, they would have equal weight, but we're going to talk about their mass. Well, then this thing will balance perfectly. Okay, we understand that. So what if? This kid on the right is huge. Well, what's going to happen to my teeter-totter? It's obviously going to tip. I would like it to balance. Yeah, maybe they're going to go up and down, or maybe this guy sends this guy airborne. I don't know. How do we get it to balance? Well, let's make it really simple. Let's say that this person is exactly twice the mass of this person. Let's say it's exactly twice the mass. Right now, the fulcrum is located directly in the center. Anybody think they have a suggestion to make this balance? And don't tell me this kid needs to lose a lot of weight. No, they're not going to lose weight. This kid is twice as big as this kid.
Professor?
What do you think?
We can move him like inwards, like more towards the center of the teeter-totter.
Okay, so you can say move this kid closer. What about the fulcrum?
Just move to the right.
Which way should the fulcrum move? Towards the smaller person or towards the bigger person if I want them to balance?
Towards the bigger person.
Towards the bigger person. Here's what it comes down to. This distance here and this distance here. For example, let's just call this, let's say this person has mass 1 and this is x1. This person has mass 2 and this is x2. There is something called the moment. The moment is equal to the mass times the distance or the displacement. In this case, it would just simply be how far away. So the moment for the first kid is m1 times x1. Now, moment doesn't have a unit. It's not like joules or pounds or anything else. It's just, we say the moment is this product. The second moment is this product. Balance can only occur if the moments are equal. That's an absolute law of physics. So therefore, you are correct when you said move the fulcrum this way. In fact, how far should I move the fulcrum? I should move it until x1 is exactly twice x2. Because if this person weighs twice as much, but this person has twice the distance, then I will get perfect balancing. So if anybody has ever tried this, you want to, let's say there's a really heavy rock and you want to be able to lift it up. So you move the fulcrum really close to the heavy rock and you get some solid rod that's not going to break. Basically, you can pry up the rock because as long as the distance and the mass you're applying is equal to the distance and the mass of the rock, you'll be able to move it. It's a really cool thing. It's a simple rule of physics, though. Balance can only come when the two moments are equal. So in this case here, the fulcrum will be placed at the center of balance, which in this case clearly would be closer to the bigger person. So now let's go back to my picture here. Let's make one simple assumption here. Let's assume there is actually a center of balance. That's really not going out on a limb. There absolutely has to be a place that is the center of balance. Now, I don't know where that place is. Let's just say hypothetically, let me just put my fulcrum down here. It's right here. Let's call that X bar, that coordinate, where my fulcrum is going to go. I want to balance all of these masses. Maybe they're people in desks. I don't know. I want to balance. So that means that the moment to the left must equal the moment to the right of that. So let's figure out what that is. Now I have a y-axis here that everything's being measured from. Okay, no problem. So what I've got then, excuse me, is I've got m1 times x1 plus m2 times x2 plus, and so on, m3 times x3. Well, I'm just going to keep adding them because for all of the x values to the left of x bar, or actually, you know what? I'm sorry. I'm sorry. I'm getting ahead of myself here. Sorry. Let me back up a little bit. M1 times x bar minus x1, sorry, plus m2 times x bar minus x2, because that would be the distance, okay? And I'm going to keep going. Oops, minus x3, dot, 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 x bar minus x n, and I have mn. Now, for every x value to the left of x bar, this is a positive value. But for every x value to the right of x bar, down the road, those are going to be negative values. What must this add up to then? Anybody want to try that? What does this total have to
0?
add to? It has to add to 0 because the stuff to the left of x bar will be positive, but the stuff to the right of x bar will be negative, and they have to be exactly 0 if that is in fact the balance point. See, I don't know where the balance point is, but I know wherever the balance point is, everything to the left will have positive, everything to the right will have negative because I'm subtracting in the opposite order. It has to add to 0. No way around it. And with that, it makes it very easy for me to find x bar now. So first thing I'm going to do is I'm going to distribute. I'll have m1 x bar minus m1 x1 plus m2 x bar minus m2 x2 plus all the way down to mn. Oh, I lost something. That's x bar. Oh, no, I got it. That's right. Mn, getting ahead of myself. I can't see very well. Mn xn. Okay. So I just distributed everything. Why don't I throw all the negatives on the other side of the equal sign? Then I would have m1 plus m2 plus all the way up to mn x bar. That's the stuff on the left-hand side. Everything else I'm going to throw on the right-hand side. Okay. Now, look at that quantity right there. The sum of all the little m's, isn't that the total mass? That's the total mass. So I'm going to put total mass times x bar. And what do I have on the right-hand side? Well, m1 x1 is that moment plus that moment plus that moment. This is the total moment. I got the total mass times x bar equals the total moment. That means quite simply that x bar is the total moment over the total mass. And the way we indicate that symbolically, this is a terrible idea. I wasn't there when the World Math Council decided this. We always use a little m for mass, and we always use a big M for moment. Not a big fan of using the same letter of the alphabet to represent two different things in the same context. So we usually use capital M for moment, little m for mass, but that's just what we've always chose. Oh, well, okay. Now, is it that simple? Yeah, I add up total moment divided by the total mass. How do I know that's an x coordinate? Because moment was distance times mass, and now I'm dividing that by distance, or dividing that by mass, excuse me, I'm leaving just the distance, the x bar. So this actually turns out to be a very, very simple thing. But that's because my mass was individual discrete mass points. Last day, remember, we said, what if the mass is variable, right? What if it's, or it should say the density is variable? What if it changes throughout? Then that requires integration. But that's still not a hard concept. So let me get rid of this picture. And let's go to the next picture we did, which was the thin rod with density delta. Okay, and like I said before, let's imagine we're on the XY plane. And so that would be, let's say, A, and that would be B. Okay, so last day we saw that the mass was simply the integral from A to B of the density dx. Okay, now how do I find the moment? Well, we know that the moment now is the distance times the mass. So if I split this thing up into a whole bunch of little pieces, think Riemann sum kind of stuff, okay, then any individual one is going to be its mass times its distance. So the only thing I have to do is add the x in this. Okay, the mass was the density integrated dx. Now it's distance times density integrated dx, because again, that produces the mass. The x has to be inside the integral because the x is not a constant. So the mass, the moment, and now if I want the center of balance of this thing, I would take this divided by this. But I'd have to calculate those integrals first in each case. So again, this is not all that complicated. But we live in a 3D world. We're not going to deal a whole lot with one-dimensional objects where we're finding a center of balance. Now, there's nothing wrong with me asking where's the center of balance on this pin if I assume, right, density is only moving left to right, not up and down, but probably safer to look in a higher dimension here. So let me get rid of this. Okay, this is our setup. But now we want to extend it one more time. And now I want to talk about a two-dimensional object like we did last day. Last day, we figured out how to find the mass of a two-dimensional object. Now we want to find the center of mass of that same object. So we said this is y equals f of x. This is y equals g of x from A to B. And we said we had density. And remember, we said density only changes left to right. It doesn't change up and down because that would mean we have too many variables involved. Last day, we figured out how to find the mass of this thing. And if you remember, last day, we showed that the mass was equal to the integral from A to B of the density portion times the area. Okay, it's a fairly simple notion. Now what we want to figure out is the moment. Except, wait a minute, we had a moment this way before. Will we also have a moment this way? Yeah, actually we will, because now my center of balance, think of this as the two-dimensional object, my center of balance will have an x and a y coordinate. Oh, that means I'm going to have an x bar and a y bar located somewhere in here. Okay, now it's really important that I understand that there's two different things I have to calculate that are separate. So that means there's two different moments. So here's how we generally measure the moment. In the X direction, I'm measuring the distance from the Y axis. That means I'm going to have a capital M with respect to the Y axis and a capital M with respect to the X axis. What's confusing is the capital M with respect to the Y axis involves the X distance, because X is the distance from the Y axis. Therefore, this guy's measuring the Y distance from the X axis. So it's easy to see how those can sometimes get backwards. Then X bar becomes this, Y bar becomes this. Okay, we're going to go through the process and derive these in just a moment. Okay, very important. Again, sometimes it can get confusing, but it's what am I measuring? Again, I'm measuring X distance. So here's what we're going to do. Let me take an arbitrary strip. Okay, and I want to find the moment. Now remember, density is only changing left to right, so up and down this strip is uniform. The density here is exactly the same as the density here and every point in between. Now, from one strip to the next, it's going to change, but within that strip, the density is not going to change. So I want to find this. We'll call that xi. Okay, that thickness, clearly that's going to be a delta xi. And that area, we'll call it the ith area, would be f of xi minus g of xi, that's the height, times delta xi, okay? Think Calc 1 a little bit. So this is the area of that strip. What is the mass of that strip? The mass of that strip we know looks like this. So let me write now the ith mass will be the density times this. Now I don't feel like rewriting that. And finally, the moment to the y-axis of the ith strip is distance times mass. So that will be density times the x coordinate times that area. Next thing comes along is I take the sum, take the limit as the norm of the partition approaches 0, and eventually we write the integral. Okay, I'll write that down, but you don't really need to do that if you remember. So if I said now I want the sum of all these guys, so the sum from equal 1 to n of delta xi, and then the ith area, which is that part right there, f of xi minus g of xi, delta xi. Boy, this gets kind of busy. Now when I take that limit, I get the integral. What is the integral that I'm going to get? Well, I don't need to take the limit. I can just go directly to the integral. So the integral for the moment versus the y-axis ends up being the integral from a to b of all of this. So density times x times f of x minus g of x dx. By the way, notice that is exactly this multiplied by x. It's like, oh, okay. After all of that, that's the moment to the y-axis because it involves the x distance. That's the easier of the two to understand. The one to the x-axis is just a little bit trickier, okay? So let me see, I think I can, let me go up here. Now, here's our dilemma. I now want to go this way. But how do I go this way? I need the y distance. Well, the x distance was easy. I'm going the x distance from the strip, but the y distance, am I measuring from here or am I measuring it from here? Well, if this entire strip is the same up and down, imagine I'm going to take you where you are and I'm going to shrink you down to 1 point, but you have the exact same mass. but I'm going to shrink you down to 1 point, literally. Okay. If I shrink this down to 1 point that's located directly in the center, or one little piece, think about it this way, located directly in the center. Think of that as the average. Okay. Then the moment to the x-axis would be that distance. Okay. That's all I need to do. This is equivalent to just shrinking that to 1 point. Okay, not a problem in that case. So I can now state, yeah, we'll do it like this. The moment xi would be exactly this. Okay. I'm still doing that, but now that would be a yi, area I. Now, we only have one really teensy problem here. I can't go directly to an integral. Anybody want to tell me why I can't go directly to an integral? What's the problem here? Everything I said is correct, but I want to do an integration. You remember this from Calc 1, hopefully, when we did areas and volumes. What's the problem with using
There's an
the
X
y?
and a Y.
I have an X and a Y. Yeah, it's not possible. I can only do one independent variable. I cannot have two variables simultaneously at the same time. Ugh. But it is the Y distance. Oh, but wait a minute. It is the Y distance. That's true. But I just said it's exactly the same as if you just shrunk this to a point in the middle. What is this distance exactly? In other words, how far away is this? Wouldn't that be exactly the average of F and G? Does everybody see that? This Y distance is exactly the average of F and G. Oh, so YI would simply be half that sum. Again, because density did not change vertically, it's as if all of it was located in the middle, and that distance would be the average of these two. That's what it comes down. That is not inherently obvious, I don't think at all, but that's what it is. So that means in the formula for mx, I'm going to need to back up a little bit here because this one's a little bit longer. So the moment to the x-axis looks just like the moment to the y-axis at the beginning and at the end, but instead of an x, we have this. We have 1/2 f of x plus g of x. That serves as my y distance. Then I have the area portion. Wow. Now that looks big and scary, but actually the f's and the g's you're going to use are typically going to be really simple, lines, parabolas. They're usually going to be relatively simple shapes. Okay, it's just not going to be that big of a deal. Okay, so when you do this problem, this will probably be something relatively small. It's not going to be huge. Now, I have to find each of the pieces. I have to find the two moments and I have to find the mass, and then I have to take the quotient. When we do this in 3 dimensions, turns out there's a third moment because there's an x, a y, and a z. That problem's a little bit bigger. It's a little bit longer, but it's, it's not terrible. So let's do an example, okay? Now, I think we did a problem yesterday. If I remember correctly, I want to use the same problem because we already did some of the work. So now what we want to do is, let's see. The region bounded by y equals x squared and y equals square root of x has density. What did I use yesterday? Did I use 2x? Does anybody remember? I think I used density 2x. I'm not positive though.
Yes, you use density 2x, sir.
Okay, has density 2x. I kind of want to use the same problem because we can then use the same mass. Here's what we want to do now. Find the centroid. That's the same as saying center balance, center of gravity, center mass. Those are all the same words. Find the centroid of the region. The first thing you must do in every problem, you gotta draw the picture. Because if you don't draw the picture, you may not get the boundaries correct. And what I mean is, when I sit on my integral, I need to know what's the top, what's the bottom, what's the left, and what's the right. If I try to do this in my head, I may not set it up correctly. So we did this problem yesterday. Okay. I know that intersection 1, 1, that's 0, 0. And because my density is a function of X, I need to do vertical rectangles. If my density was a function of Y, then I would do horizontal rectangles. But we definitely need it like this. Okay, so we saw last time when we did this, little m. So the mass was the integral from 0 to 1 of, remember, density times the area. And the area was square root minus parabola. So x to the 1/2 minus x squared. And again, we did this yesterday. Did we get an answer for this? Do you remember? Did we save ourselves some time? Did we get a number? I think we did.
11 over 20 units.
We got 11 over 20. Thank you. I need all the space I can get. Now, we did this problem last day and we stopped here because that's all we knew. Now I want to find the center of mass. Do you agree that the center of mass of this shape ought to be located inside the shape? Does everybody agree with that? That my center should probably be inside of this thing? What do you think? Does that seem reasonable?
Yes.
So at the end of the problem, if my center of mass is over here or in the second quadrant, probably means I have an error. It is reasonable to say, yeah, the center of mass is probably located inside that shape. By the way, I will show you that sometimes there are exceptions to that. But looking at this, yeah, I'm pretty certain it's going to be inside here. That will help me check my final answer, by the way. So now the moment with relation to the y-axis is exactly this with a multiplier of x. Okay, I'm going to take this quantity and multiply it by x. Oops. Oops. Try that again. And there we go. Visual aids here. Okay, and I can combine terms there. So 2x squared times this, that would be 2x to the 5/2, and then 2x squared times this, that'd be minus 2x to the 4th dx. Okay, and then that would be x to the 7/2 times 2/7 times 2, and then x to the 5th times 2/5 from 0 to 1. So I've got 4 over 7 minus 2 over 5. So that'd be what, 6 over 35. Okay. In and of itself, that number doesn't mean anything to us yet. That's just the moment. We're going to put it together with the mass at some point. Now, lastly, the moment related to the x-axis, it's exactly the same thing, but now I put a y in there. Oops, but I can't put a y. So what does y become? Y becomes the average of these two functions.
Professor,
Yes.
we can see your ceiling fan right in the middle of the board, and it's making it hard to see what's written down.
Oh boy, that's here's the problem is I can't really do that. That's yeah. Well, you know what? Worst comes to worst, I will talk and tell you what the numbers are. So 2x times x, x to the 1/2 x squared. So I'm taking the mass and I'm basically just inserting an x. Now I'm taking the exact same mass equation, and instead of inserting a y here, I'm inserting the average of the functions. Everybody got that? Yeah, I apologize, but I can't do much about the glare. I tried to do that yesterday. I actually took out some light bulbs and it really didn't help. So right here, I now have 1/2. Actually, I'll write it in the same order as those two. Sorry, I have it as x to the 1/2 plus x squared. And then that part is being multiplied by the area portion, which is the x to the 1/2 minus x squared dx. So at this point in the game, this looks big and scary, but these things actually multiply out really nicely. In fact, you notice that these right now are conjugates, aren't they? A plus b, a minus b, doesn't that give me a squared minus b squared? So this part here multiplies out really, really nicely. I have the 2, I have the 1/2. What is this going to multiply out to? Well, what's x to the 1/2 times x to the 1/2? What is that? Anybody?
X 1/4.
Not quite. What do we do with exponents here? What's x to the a times, times x to the b? Isn't it x to the a plus b? I add exponents. So what's square root of x times square root of x?
1
That's just
x.
minus x to the 4th. Oh, times that x, this actually is quite friendly. So this is going to be 0 to 1 of x squared minus x to the 5th when all is said and done. Wow. So that really scary looking thing reduced tremendously. So then that ends up being 1/3 x cubed minus 1/6 x to the 6th from 0 to 1, or 1/3 minus 1/6, which is just 1/6. We now have every piece of the puzzle that we need to finish the answer, which is at this point relatively simple. Let me go ahead and erase this. Remember, the lecture is recorded, so you can always go back and look at stuff. So x bar. X bar is the moment to the y-axis, because that involves the x distance, that number, over the mass. Okay, now all you need is a cheap calculator with a fraction key. Now, I can do this in my head. I'd rather just use my cheap calculator. All right, so 6/35 over 11/20, and I come up with 24 over 77. Okay, y bar, which would be 1/6 over 11/20. And that is 10/33. Now, that's a little bit less than a third. That's a little bit less than a third also. Did everybody see that? So in my incredibly accurate computer-generated drawing in front of you, that's 1 unit. So we're saying our center of balance is probably around there. I think that's what we're saying, if we did this correctly. Interesting. I would have thought it was further to the right personally, but it looks like that's what we got. Okay. Now, is it located inside the shape? I think it is. Because if I just said right down the middle of the shape is the line y equal x, my x and my y are pretty close together. So I have a little bit of faith there. Now, there's nothing about the answer that's important. It's really the process. I have a 2-dimensional closed shape that does not have constant density. The only way I can find the center of mass, or the centroid, is to integrate. But it requires 3 integrations, 1 to find the mass and the other 2 to find the moments. And then I answer the question. Let me ask you a question. Can mass be negative? Is there any way I can produce a problem, have a problem where the mass is negative? No,
No.
no, that's impossible. Can a moment be negative?
Yes, maybe.
Give me an example.
I'm just guessing.
No. Where's my region right now?
It's
In the
inside.
first it's in the first
Yes.
quadrant. What if my region was in the second quadrant? Wouldn't my x coordinate have to be negative, my x bar? So think about this logically. If mass has to be positive, a negative moment would mean I'm in a different quadrant. In the third quadrant, both moments would have to be negative. In the second quadrant, the y moment would be negative. In the fourth quadrant, the x moment. So a moment can be negative because that's how I can get a negative x bar or y bar, being in a different quadrant. If I'm in the first quadrant, then everything's clearly going to be positive. But if I'm in a different quadrant, I can get negative moments. I cannot get negative mass. By the way, will people turn in a quiz with negative masses? Yes, probably half the people will have a negative mass. How could you get a negative mass? Subtracting in the wrong order because we didn't draw the picture first. Believe it or not, I get more negative masses than I do positive masses when people turn in work because they tried to do it without a picture. So they subtract in the wrong order because they had the wrong curve on top. If your calculation produces a negative mass, you don't just fudge it and say, oh, I'm gonna make it positive. Because you might have gotten a negative because you actually have an algebra error. You subtracted that, you just made an error somewhere and you got the wrong number. But a negative mass is impossible. You got to go back and revisit the problem. But a negative moment is totally okay if I'm in a different quadrant. Now we're in the first quadrant, so that's why I said everything should be positive. Now, I asked the question because center of mass is actually considered one of the more important applications in all of calculus because it applies to real life. It applies to anything we're going to be building, any type of construction. We spend a lot of time on this in Calc 3 because we can do more problems. But a center of mass, I have a hula hoop. Everybody knows what a hula hoop is, right? I have a hula hoop. It's a solid ring. Where do you suppose the center of mass of this thing is? If I laid down my solid ring on a gigantic piece of cardboard, where would I have to put my finger to balance that piece of cardboard? Do you agree it'd probably be right at the center of the circle? Does that seem reasonable to you? It'd be a pretty terrible hula hoop if the center of balance wasn't at the center, you know. It's a really distorted, warped hula hoop. But I think most of us agree, yeah, the center of balance is probably the center of that circle because the hula hoop is circular, okay? If I lay it flat on a piece of cardboard, then I'm probably gonna have to put my finger in the center of the circle to balance that piece of cardboard. That makes perfect sense. That center of balance isn't part of the physical shape, right? It's in the middle. Now, if I filled in the circle, okay, then that's easy to see. But I'm pointing that out because sometimes the center of balance of something isn't located as part of the physical shape. Anybody here play horseshoes? Never? You guys know what a horseshoe is, right? It's the
I
symbol
played
on
horseshoes.
yeah, it's a symbol on the Colts helmets. A horseshoe looks kind of like this. And your horseshoe might be solid metal. So this thing has thickness to it. This is a thick, and you hold it and you throw it at a ring and all that stuff. Now, I want to lay my horseshoe flat on a big piece of cardboard, and I want to balance it with my finger. Again, probably somewhere around here is going to be the center of balance. Again, the center of balance is not located physically as part of the horseshoe. But it is located inside. In other words, it's not out here somewhere. So generally speaking, if you have a closed shape, your center of balance is going to be in the shape, in the middle of the shape somewhere. This isn't quite closed, but the center of balance is still located kind of in the middle there. Okay, it's not located on the outside. That's important to recognize. So you're going to do a problem, usually a relatively simple set of boundaries, you know, lines, parabolas, things like that. You came up with your center of balance and you're looking at your shape and you're maybe plotting the point and going, you know, my center of balance is completely outside the shape. So, you know, in the XY plane, I had something like this, and my center of balance was over here. Probably not good. My center of balance probably should be somewhere in there. Okay, now if it's getting more dense as I move left to right, then the center of balance is probably more on the right. Doesn't really matter. But it shouldn't be outside the shape. It shouldn't be in a different quadrant than my shape. That would be even worse. Yikes. Okay, now before I move on, go back. I'll review for just a second. Does anybody have any questions on this stuff? Because we're going to move on in a moment to the next thing. So center of balance, center mass is actually a fairly simple notion that I'm trying to find the one point that's a balance point. Our serious restriction is that from left to right is the only way we can change density. Realistically, I ought to be able to have a different density at every point, but that would require multiple variables. That's Calc 3. That's not what we can do in our class, unfortunately. Okay, so we'll move on to the next thing. This is also considered an important application, kind of similar to the work problems that we did yesterday. We're going to look at what's called fluid force. Now, think swimming pool. All right. I have a swimming pool, and let's say my swimming pool is angled downwards. Okay. You know, I have a deep end and a shallow end, and now I'm filling it up with water. It's actually not that difficult to measure the force of the water on the bottom of the pool itself. That's actually not very difficult, because literally I'm just taking the weight of the water. So if you've ever looked at an old swimming pool, there's usually a lot of cracks and things like that, and that's again just because of the weight of the water. Now, if anybody here ever swims on a regular basis, and let's say you're going to the deep end of the pool, you know, maybe you're down the bottom of the deep end of the pool. Why does it feel like there's a bazillion pounds of water on your head? Anybody know why do you feel like that?
Pressure?
Because there's a bazillion pounds of water on your head. Yeah, water is very, very, very heavy, and you're feeling that. So pressure is one of the key words. There's a few different words that we're going to have here. Now, when you're near the surface of the water, do you feel a lot of pressure near the surface? Probably not. What changes the pressure?
The depth.
The depth. Yeah, depth is extremely important. That's one of the major things. There's pressure, there's depth. Now, what about the fluid? Okay, we'll call it the fluid you're in. Water has a certain amount of density. It weighs a certain amount. But are there liquids that weigh more or less, perhaps?
Yes.
Yeah, all liquids do not weigh the same. How do you know? Well, if you pour oil into a big, tub of water, does the oil sink? Does it mix with the water, or does it float to the top? Think about that. What does the oil do when you pour it into the water?
Float.
It floats. Why does it float?
Since they're different densities, they can't mix.
Okay, back up.
Or-
They can't, maybe they can, maybe they can't, I don't know. Oil and vinegar, we can mix those for a moment. But you said something about different density. Yes, the oil is much less density, therefore the same amount of oil in water, the oil weighs less. That's why it floats to the top. You're gonna go swimming in the water. You hold your breath, you jump in the water, and of course you immediately sink to the bottom, correct? Or do you tend to float? What do you tend to do? You individually, do you tend to float or do you sink?
Sink, because I don't know how to swim.
Your lungs are full of it. Take a
I
big
sink
breath.
unless I'm flat.
Most of you probably float to some degree, I'm guessing. Yeah, to some degree. Personally, I'm different. I can fill my lungs with air and lie on the bottom of the pool until I run out of air. I can't hold my breath for 2 minutes, but I can hold my breath for a minute. It always kind of creeps out lifeguards because I'll be lying on the bottom of the pool and every now and then you'll see a bubble. Now, most people can't lie on the bottom of a pool with their lungs full of air. I can't float if my life depended. I have to swim. I'm a certified diver. I haven't dove in many years. And when I was doing my diving test, one of the parts of the diving test, you had to do what's called a 10-minute float. So you have to be out in the middle of the pool and doing nothing. You know, you could be out in the ocean and your boat capsized. You have to be able to stay alive, in other words. And during that, everybody's out there floating, and I'd be standing at the bottom of the pool. It was a deep pool. And every, minute or so, I'd launch myself to the surface of the water so I could get some air. And then I'd immediately go down to the bottom of the pool again. They didn't really know how to deal with that. I passed my test. And then when you get your big, thick neoprene wetsuit, the diving suit, most people wear 23 or 24 pound weight belt. That's to balance the buoyancy of the wetsuit. I wore a 12 pound. Because if I wore the 24 pound, I sunk to the bottom of the ocean and it was really hard to get back up. Now I'm like a lead weight. Why? Because my body physically is more dense than water. Most human beings are less dense than water. That's why they float. It's a crazy idea, but that's why the oil floats. Now, you say, but I always sink. But if you filled your lungs with air, you might not sink, because air, right, is very, very light. And when you fill your lungs with air, you're making your overall self less dense. It's some cool physics going on in there.
Interesting.
Yeah, it's crazy. It's crazy cool. I had to learn
how to float. I'm like, why can't you float? And I'm like, relax. If you get more pressure, you like putting yourself. I'm like, that's why you can't float.
Well, and also if you expel all the air out of your lungs, you tend to sink. Now, fluid force. We're gonna use water as an example, but we're not always going to use water in calculations, because water is not that friendly when it comes to the calculations. The numbers for water, whether you're using English Standard or metric, doesn't matter. Water isn't the friendliest when you're talking about weights and things. So a lot of times I'll just say we have a liquid of a certain density, and they'll make up a nice, really happy round number to make our life easier. But the idea is, I want to find the force of the water. Well, force vertically is easy. That's equal to weight. So instead, here's what I want you to think of. Okay, whatever room you're in, you're going to seal that room up. You're going to bring in the water hose, and you're going to fill the room up with water. In theory, not in practice. I can measure the force on the floor. What I'm asking is, what is the force on the wall? Oh, what is the force on the wall from the water? Now, that's an interesting thought. On the wall. So if you look at your room, however big your room is, and take this wall that's nearest to you. Now, if I fill it up a lot, well, there should be more force against the wall because there's more water, touching the wall, that kind of thing. Now, think about going away from the wall. Maybe you're in the middle of the room. Is the water in the middle of the room pushing against the wall? Think about that. Is the water in the middle of the room pushing against the wall? The water that's several feet over there, is it pushing against the wall?
I would say yes.
Well, that's a tricky one. Let me give you a simple way of thinking about it. I'm going to build a little mini wall about a foot from this wall. Okay, I'm going to build a little mini wall about that far, because I don't want to waste water. I hate wasting water. I'm going to build a little mini wall, and then I'm going to fill up that space with water. Rather than fill up my whole room, because that's a lot of water, and I don't want to pay that water bill just for a math experiment. So I'm going to build a little teeny wall a foot away from the wall, and I'm going to fill that in between. I'm going to fill that up with water. The force against the wall is exactly the same as if I filled the entire room up, because it's only the water that's actually making contact with the wall. So the water in the middle of the room or the other side of the room actually isn't making contact with the wall. It doesn't matter how long the room is. That affects the force against the floor because there's a lot more water, but it only affects the force against the wall is the water that's actually touching the wall, quite literally. That's something that's not always common sense. So the idea is, okay, let's say here's the water, and I have something, in this case here, what we're going to do is we're going to have something that's we're going to do horizontal rather than vertical. Why? Because the force does not change left and right. The force is only going to change up and down. We kind of know that. So the force on the wall here versus the force on the wall a foot to the right is the same. But the force on the wall a foot above and the foot below, that would be different. Again, because gravity. So the question is, how much force is on that strip? And eventually I can add them up. Well, somebody mentioned two words earlier. You guys mentioned pressure and you mentioned depth. So the first thing we have to discuss is the density of the liquid. But now we're going to use a different form of density. If you remember last day, I said density technically has 6 versions. It's mass per unit length, area, and volume, but it's also weight per unit length, area, and volume. So if I'm talking about the density of water, for example, we say things like pounds per cubic foot or pounds per gallon or newtons per cubic meter or newtons per liter. We use terms like that. In other words, we use weight per volume. Okay, so the density of a liquid, we don't use mass. Well, no. We don't use mass. We will never get force if we use mass. We need to use weight because weight is force. So the density here would be weight per volume. Okay, now what is pressure? Pressure. Ooh. If I said I'm going to go underwater on the top of my head, I feel a lot of pressure. Because the top of my head, think of my head as being flat. I'm feeling a lot of pressure. When you fill up your tires, what is the unit of measure when you're filling up your tires? Anybody?
PSI.
What are the initials? PSI. What does
Pounds per
PSI
square
stand for?
inch.
Pounds per square inch. Pressure is weight per area. PSI. Pressure is weight per area. So if I'm feeling a lot on the top of my head, it's the area of the top of my head and the weight of the water on it. That's what the pressure is. Now, what are the lengths of, what is the unit of depth? Depth is just length, isn't it? It's a length unit. So what's the connection between these three things? What does pressure equal? Equals depth times density. You can see that from the units. If I take weight per volume and I multiply it by length, I will now get weight per area, right? One degree less. Now, what is pressure? We said pressure is weight per area. So how do I get fluid force in general then? Fluid force is simply the pressure times the area, which is equal to depth times density times area. We can see that from the units. That's why last day when we talked about units, it's so important that I understand. So if I want to find the force of a fluid at varying heights, I need the depth, I need the density, I need the area. Now, density will always be a constant. You don't calculate density, you're given density. What's depth? Depth would be that distance right there. We'll call that yi, that's our depth. Our area would be this area right here, which is going to be something. We'll call that thickness delta yi. And a lot of textbooks will say length. I like that. Just the length of that strip times the thickness of that strip times the depth of that strip times the density of the liquid. That's how I'm going to get my force. Now, depth is kind of a tricky one. If this is the surface of the water.
Professor,
Yes.
can you quickly repeat what it says on the, because the glare, I can't see what it says next to the, on the right side of the square?
Here?
The little more to the center, like what does it say right there? Yeah,
Oh,
right.
this is length. All right.
But then sorry, because the glare, I'm like, I can't see what that says.
No problem. That's the length of that strip times the thickness of that strip.
Oh, okay.
That would be the area of that strip. And that's the part that's also going to go in the integral at some point. Now, depth is a tricky one. If this is the surface of the water, are these negative numbers? Or do I start with 0 and say these are positive numbers? Now I'm going to give you a simple example so you guys can tell me the answer. You're going to go out swimming in the ocean. Maybe you're out in a boat. You go out a little ways in the ocean. Maybe you're diving. Maybe you just want to swim in the ocean. So you're out there. You're a good swimmer. You're swimming in the ocean, and the water is, it's deeper than 6 feet deep. You're out a little ways. If I said the water was 10 feet deep, you go, okay. If I said the water was 1,000 feet deep, would you start freaking out? You're at the top of the water. Does it matter how deep the water is if you're at the top of the water? I guess if someone tied, lead weights to your shoes and you sunk, yeah. But I'm saying when you're swimming on the top of the water, does it matter how deep the water is?
No.
Not really. You say, well, today I went, I went diving today and I dove 50 feet deep. Does that mean you went 50 feet from the bottom of the ocean, or does it mean you went 50 feet from the top of the ocean?
From the top.
Yeah, we never measure from the bottom up. The bottom could be 10,000 feet down. You don't measure from the bottom up. Oh, today I went diving 1,500 feet from the bottom of the ocean, but that doesn't tell me how deep you were. We measure depth from the top down, and here's what's weird. This is 0, and we measure positively in this direction. If I say, how deep did you go? You don't say I went negative 10 feet deep today. You said, no, I went 10 feet deep. That means I went 10 feet below the surface of the water. So depth is one of the weird things. Positive, we go this way. Does everybody understand? Because otherwise we'd have negative values in our calculations, which would be, well, it'd be crazy. Why even do it? So we measure depth from the top down positively. So if I'm 5 feet deep, I'm 5 feet from the top. I don't say I'm 5 feet from the bottom going up. You could do that, but it requires more information. When I'm out diving in the ocean, I don't need to know where the ocean floor is relative to where I am. I need to know where the surface of the water is relative to I am. Okay. So with this said, this is what we need in order to do the calculation. Now we're going to do a really simple example. This is one of my favorite ones because it brings up a little bit of review at the same time of integration. All right, so off of Point Loma, there is a gigantic, basically it's like a tube. What's the term I want to use? It's sewage and things like that, but it goes out a few miles, and it's, that's where they dump a lot of the bad stuff, but it's really, really, really long. Now, it could be sewage, it could just be a way of transmitting water and so on. So here's the thing. You've got this really long tube. And let's say the tube is half filled with liquid. And we'll discuss what liquid we want to use. It's half filled. I would like to know what is the force at this end. The tube is closed off. We have it closed off. I'd like to know what is the force at this end. Does it matter how long the tube is? If I'm calculating the force on this surface, on this face, sorry. Does it matter how long it is? Remember, if I'm calculating the weight, then it would matter how long it is. But I just want to know, let's say on the other side of this, I have fluid on the other side of this pushing against this wall. It only matters how deep it is. It doesn't matter how far back it goes. That's the weight of the stuff. I want the force against the wall. So all that matters here is really the area of this. It doesn't matter how far it goes back. Again, that kind of defies common sense at first. The longer the tube, the more the weight of the liquid, but it doesn't affect the force on this part here. Again, only how deep it is affects the force on this part here. So let's suppose, okay, so what we have is a tube of diameter, let's say 4 meters. This is huge. Diameter 4 meters, and let's say it's 20 meters long. Okay, it is half filled with a liquid. Okay, it's half filled with a liquid that, let's say, is 10,000 newtons per cubic meter. And that sounds like a lot. Water's about 9,800 newtons per cubic meter. So that's a tiny bit heavier than water. It's dirty water. I tend not to use water all the time because the numbers for water aren't very friendly. Just so you guys know, a lot of times we do these problems. I'll do the problems with pounds per cubic foot. I might do the problem. I don't use pounds per gallon because gallon doesn't help me with area. But pounds per cubic foot, water is about 62.43 pounds per cubic foot. Most calculus books will use 62.5. How come? Because 62.5, if you double, it's 125. If you double, that's 250. If you double, that's 500. 62.5 is 1/16 of 1,000. It's a really nice, happy round number that makes calculations so friendly. Problem is, it's not the right number. Oh. So if I'm using water in English Standard, it's 62.43 pounds per pounds per cubic foot. If I'm using metric, it's about 9,810 newtons per cubic meter. I think 9.81, right? That's meters per second squared. That's gravity, and then you're multiplying it by the mass. Neither one of those numbers are entirely friendly. So I never use water. I always use something that has happier numbers. So we have dirty water. So dirty water has a much nicer round number here. My question is, find the force on this face right here. I want to know, what is the fluid force? Now, can anybody tell me the units that my answer is going to be in? Not the number. I have no idea what the number is. We have to calculate that. What will the units of my answer be?
PSI?
Remember, I'm saying the force.
Newtons.
Newtons, because that's the only force in the problem. This is the density, newtons per cubic meter, but in the end, newtons are the only force unit. If this were pounds per cubic foot, then your final answer would have to be in pounds. We're not finding work, remember, we're finding force. So we must use force units. So in this case, it makes it easy because the only force unit in the problem is newtons. So what I need to do is set up a calculus problem. Well, how am I supposed to do that? I have a circular face here, it's half full. Why don't we make an XY plane? Okay. Where should my x-axis be? Anybody, any ideas? Do anybody see any obvious places? I can put my x-axis right here. I can put it right here. But maybe if I put it right here, that might work really nicely. It's a circle. Therefore, where should my y-axis probably be? Here? Here? Or right down the middle?
Through the center.
Yeah.
In the middle.
Then the center of my circle would be the origin of my x. Oh, why is that a good thing? Because now my circle will have equation x squared plus y squared equals radius squared. Oh, well, that makes it easier. But I don't know what the radius is. Or do I? What's my radius?
2.
2. So what goes here?
2 squared.
2 squared or 4?
Yeah.
Oh, well, that's not so bad. Okay. See, you in real life, you're never given the equation. You're given the situation. You're given the problem. You've got to do the math. You've got to create. We created this out of our convenience. Could I have put the center of my circle somewhere else? Could I have put it here or here or here? Yeah, I could have put it anywhere. Right there is the most logical place because it makes describing my boundaries much, much simpler. So let me take an arbitrary slice. Okay, now remember, depth, that's the depth. We'll call that the yi. That's the length. Well, let's see. That's the x distance, agreed? So wouldn't that be 2x from here to here? Does everyone agree that that would be 2x? If from 0 to the edge is x, all the way across would be 2x. But I need that to be a function of y. How am I going to do that? Well, wouldn't x squared equal 4 minus y squared? So x would be the square root of 4 minus y squared. And the positive, because x represented a positive number. Oh, okay. So that distance across would be 2 times that. Now, the force on this strip. So we always start right, with the one strip before we do the integral. The force on that strip, the ith force, I said was depth times density times area. You remember? Well, I'll put that in front times the depth and then times the area. How about if I write it as 4 minus y squared to the 1/2 power? Okay. Now, very importantly, what is the range of values for y? This is not tricky. You have a circle of radius 2. Your depth at the top is 0. What's your depth at the bottom?
-2.
Depth. Hint,
Just
it's
2.
impossible. Yeah, if you said you were -2 feet deep, that means you're floating 2 feet above the water. Remember, positive is going down, so your depth is ranging from 0 to
2 feet.
0 to 2. Yeah. Why is that important? Because those are going to be your limits of integration. Ooh. Well, if that's the force on one slice, and then I take the sum and I take the limit, yada, 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 let's go right to the integral. 0 to 2 of this stuff. Of 10,000 y, 4 minus y squared to the 1/2 dy. Oh, sorry, I left out my delta y here. There should be a delta y. Okay. Now, everything I said is true. Everything I said is correct. Do we know how to do that integration? We haven't learned any new techniques this semester, so did we learn last semester how to do that integration? Anybody?
I don't remember.
All right, I did give you guys an integral sheet. This would be about as generic as any Calc 1 problem I could possibly come up with. There's only one way to do this.
Is it with U-Substitution?
U-Substitution. Beautiful. Now, because that's being raised to a power, my U pretty much has to come from there because my argument there. So let's do it. Again, I like this problem because it forces us to use a Calc 1 technique that is probably the most common one we did, integration using U-Substitution. So how about if we let U equal 4 minus y squared, then what's my du? What do I need?
-2y.
-2y dy. Do I have that? I think I have a multiple of that. If this y had an exponent on it, we're in trouble. Okay. If this y had an exponent, then this is not a Calc 1 problem. It's something we have to still learn in this class. But because this is a multiple of my chain rule factor, that's as friendly as it gets. We just have to, move the numbers around a little. Now, remember, a definite integral where you're changing the variable, you absolutely have to change the limits. You can't leave the old limits, otherwise we get an impossible answer. So right now, y is ranging from 0 to 2. What will u range from? Well, let's see. When y is 0, what's u? When y is 0, u is
4.
Bad English, doesn't it? U is. And when y is 2, u is 0?
0.
Now, before we move on, let's fix that. I need this to be a -2y. I have a 10,000. So what do I do with the rest of it? It would come out as -5,000. Does that sound about right? I'm going to rewrite it. Now, have I changed the value at all? Or is this exactly the same thing?
It's the same.
I'll take this out. But this is what I'm substituting in for. Now, a lot of people look at this and go, oh, well, that's all goofy. Yeah, but I'm also going to have a negative here, so that's not really an issue. So right now, we have a perfect opportunity to do a not terrible problem. So this is -5,000 times the integral from 4 to 0 of u to the 1/2 du. Yeah, somebody walks in the room right now and they see this and they say, that's it? That's all you got in Calc 2? I know how to do that on day 1 of Calc 1. Well, maybe. The antiderivative? u to the 1/2, so the u to the 3/2 times 2/3. So times negative 10,000 thirds. And I'm going from 4 to 0. Now, because of the negative, this answer is going to come out positive. Okay. What is 4 to the 3/2 power? 4 to the 3/2. Well, 3/2 would mean square root cubed. So 4 to the 3/2 is
8.
just 8. Yeah, that's nice. And all else fails, you can always do it on here. So that's 8 times 10,000 thirds. So my answer is 80,000 thirds. Keep going. 80,000 thirds what?
Newtons.
Newtons. Beautiful. And it's rational. Yeah, you wanted an integer, but you don't have much control over that. I like this problem because we were able to pull up some technique from Calculus 1 that is really, really helpful, and that is doing a U-sub, because that's the one we probably practiced the most last semester, and the one you're going to be using all the way through, calculus and beyond. We still want to remember how to do it. So is that a lot? Is 80,000 newtons a lot? Is that a lot of force? Well, if 1 cubic meter of water weighs roughly 10,000, this is less than 27,000. So the force on that end it's a lot, but it's not going to like bust down a building. The numbers are so huge because the conversions between newtons and English standard and stuff, I don't need, by the way, let me make it real clear. I don't need anybody here to know any conversions whatsoever. Okay. I always have fun with this because in the United States, there's always been a hesitancy and a resiliency to the metric system. Believe it or not, I believe the first time, I want to say it was 1974, before Congress was a law that the United States had to completely convert to metric by 1974. In every way, no more feet, no more miles, no more nothing. And then Congress said, no, we're going to delay that a couple years. By the way, has the United States completely converted to metric in all ways?
Everything's based on metric, but we still use the other
You
units.
guys watch football ever? I mean, last time I checked, the field's 100 yards long, and I buy my milk by the gallons, and no, there's a lot of metric in the U.S., but we're not even close because Congress keeps delaying that. In fact, I think they finally just gave up on it. Gas pumps, everything was going to be metric, and by the way, the biggest resistance, believe it or not, for the longest time came from the automakers because they'd have to retool everything. Well, they've long since done that. There's nothing in your car that's English standard. Everything's metric now. But the problem is we all know a little bit of both, but we're not really comfortable going back and forth on a large scale. And it makes it kind of difficult because a lot of times we get the units wrong. See, is there anybody in here who grew up outside the United States? In other words, you grew up in a metric, country where you used to things. You know how long a centimeter is, and you know what a liter is. A lot of students. And then one thing that always makes me laugh, I say, well, even your European countries are not close to being completely metric. You know why I know that? Because whenever I ask somebody how much they weigh, what unit does every human being on planet Earth give you when you ask them how much they weigh? And they give you kilograms, which is kind of like saying, how much do you weigh? 6 feet. How much do you weigh? 25 years. In other words, the lamest, worst answer you could probably give me when I'm asking you for your weight is something that's not weight. Kilograms is not weight. A human being cannot weigh any amount of kilograms. Kilograms are your mass. And you have the same mass on all surfaces, on every planet, and you weigh a certain amount. And I have never heard a human being in my entire life give me the weight correctly in metric, because if you were, you wouldn't be using kilograms, you'd be using what? Newtons. But most people don't have any idea how to go from kilograms to newtons. Does anybody here know? You really should if you're in physics. How do you go from kilograms to newtons? You multiply by about 9.81. It's actually that simple, but really? So 100 kilos is about 981 newtons. You can't. No. How much does 100 kilos weigh at sea level? About 981 newtons. See, you can say how much does a kilogram weigh, but a kilogram isn't weight. That would be like saying a gallon of water is weight. No, a gallon of water weighs a certain amount. So I always have fun when people tell me, no, we do everything metric except force and weight. That would be newtons 100% of the time. And even in your physics classes, they'll get guilty and they'll use kilograms. No, I was a competitive lifter for a long time ago. And so I can actually do simple conversions. I know how much kilograms weigh at different levels, but even in the contests, they thought they were way ahead of it because everything's in kilos. When you watch the Olympics, everything's in kilos, which is kind of funny because kilos aren't weight, but most people can know how much a kilogram does weigh at sea level. See, if you go to the moon, you're only going to weigh about 1/6 as much, but you're going to have the same mass. That never changes. So I always have fun with that. But again, this class is not heavy physics. It's not heavy on the units, but I do want you to get the units right. So last day we did work problems. There were only 2 units we used. Joules when it was metric, pound feet or foot pounds when it's English standard. Today we're doing fluid forces. There's really only 2 units we're going to use. Newtons if it's metric, pounds if it's English standard. And after this, we're not even going to do units pretty much the rest of the course. We're going to answer questions and we're going to do more stuff, but these are the only problems really that involve units. So you're kind of off the hook. I would like it if you went to your physics class, if you guys were the ones who did get all the unit questions correct because you actually know and understand. All right, oops. I'm going to stop the not here. So for the quiz, and this is only next week's quizzes. After next week, you're going to be handing them to me. You're going to have to submit them electronically for the next week, just simply because unless you want to drive by my house and drop it off, I guess that would work. But then I'd have to tell you where I live, so maybe that won't work. There's a very simple phone app that I used all through the pandemic called Fast Scanner. Some of you may be aware of this. There's a similar one, I think it's called Cam Scanner. Fast Scanner is an app you download to your phone. If you go to YouTube, there's about a minute and a half long tutorial on how to use it. It's ridiculously user-friendly. It's an app you put on your phone, and what you do is you go up to your quiz, you go click, 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 send. You just take pictures and you send it, and it preserves things. If you somehow take a picture and it comes out sideways, which about half of them do, I can rotate it. If it's too small, I can enlarge it. If it's too faint, you can darken it because it has a contrast control. So I want to make sure all of you understand this. Before you send me anything, you have the ability to look at it and know exactly what it looks like at my end. So please make sure it's actually readable. If you're doing your work in pencil, for example, and you take a picture, it might be really, really light. So then you want to use the contrast control. If you're doing it in pen, you're probably fine. But sometimes you guys, when you lean over to take the pictures, there's a big shadow that you just created over the picture that you didn't realize until after you took the picture. And then you say, oh, now Mr. Brown's not going to be able to read this. So please make sure before you send it, it's really easy. If you send it in your email as part of the email itself, not as an attachment, but as part of the email, I cannot rotate it, I cannot enlarge it, and 99% of the time I can't actually read it because it's going to come out a 1x1 square. So don't send it in your email, send it as an attachment to your email. Do not convert it to a PDF. Not only does that take a lot of extra time, I'm not going to deal with it. I do not download anything that another human being sends me, ever. I get 100 attachments a day that have to be downloaded for me to open them. I don't do that for many reasons. One is not only the memory, that's how viruses get to your computer. You download something, I don't download people's stuff. Do not send them as PDFs, send them as pictures. They're basically like JPEGs at that point. I only create PDFs on quizzes and certain things when you're having difficulty opening things. Some people have really old computers and they have a hard time opening stuff that I've written in the equation editor. So occasionally I'll have to say something's a PDF. I'd rather not. It takes, again, too much extra storage and work. So the Fast Scanner app or similar apps, you take the picture, put my email address on your phone. Only send it to my email. Okay, this is the other thing some people don't realize. Canvas is a bulletin board for me to post things on so you can get them. I've never sent an email through Canvas because I do not have the ability to send an email through Canvas. I don't receive emails through Canvas. I get a notification from Canvas when I log on to Canvas that somebody tried to email me. And sometimes it'll say somebody tried to email you and there's an attachment. I will never see either thing. Don't email me through Canvas. That isn't what Canvas is for. Email me through my email, mjbrown@sdcct.edu. And then have that in your phone. So when you do the fast scanner thing, click. If you do it right, from beginning to end really shouldn't take more than about 30 seconds. And then if you're having difficulty, contact me. My strong suggestion is, okay, your quiz is due by the beginning of class. You can always turn it in early. So if you're not sure from your end if everything's working out okay, I've already got a wave of quizzes turned in on my inbox where basically people are saying, hey, can you open this? Can you read this? Can you tell me if I sent it in the right format? And right now, about 2/3 of them have, and the other 1/3 I'm saying, no, I can't see it. You sent it as part of an email and it's a 1x1 square that, by the way, is either sideways or upside down. I hate reading emails like this. It's really hard on me. So it's okay to send me anything early. I would not wait until 15 minutes before class and then try to send it only to find out you're having problems, that it's not working for you. That would be a bummer. So certainly for the first one, maybe send it a day early just to make sure that you did it right. And you're only doing it twice. You're only doing it next week on Tuesday and Thursday, because after that, again, I'm crossing my fingers, we're in class. So this is it. That's all you're going to have to do. But I want it to be simple. So again, take pictures. You do not technically have to print the quiz sheet itself. I strongly urge people to print the quiz sheet for many reasons. One is when you're preparing for your first exam, retaking your quizzes is one of the best practices. And you already have that sheet printed and you don't have to go find it. But really the more important reason is about half the people won't print the quiz sheet. They'll just write down the problems or do them separately. And of those, the majority of errors will not be calculus errors. They will be because they wrote the problem down incorrectly. And I would say upwards of half of all the people who don't print the quiz will have at least one problem. They just simply copied the problem incorrectly because they don't have the problems sitting right in front of them. They wrote them down. Yeah, so that's a reason that you might want to print the quiz. So then you absolutely have the correct questions, plus you then can use it later. Okay, that's, again, I don't need you to turn in the quiz sheet, but you probably want to have it. Please make sure your name and ID number are clearly identified on the quiz sheet. And I'll send a reminder email over the weekend to everybody. Just remind, hey, don't forget to turn these in, name and ID number. And when you're sending it to me, so Laylee's sending me her quiz, it should just simply say, quiz 1, but in the subject line, put math 151 quiz 1. Remember, I have a lot of classes. And because not all the quizzes are turned in at the same time, I might have 30 quizzes in my inbox when I log on from 4 different classes. It just makes it easier on me if I know which class each one's coming from, then I can kind of group them. So when you're sending it in, make that fairly clear. All right. Is there any question?
What, like Tuesday, Thursday? Do you have any other math 151, or are we the only one right now?
You're the only 151. I have a
Okay,
252. I have a 254. I have a 119.
Okay.
So
I'll just
you don't need to say Tuesday, Thursday. Just say 150.
Okay. Thank you.
When I get the email, unfortunately, I don't know everybody yet. So when I see Laylee, it doesn't automatically hit me. Oh, Laylee is that cool chick in my 151 class who always gets everything right. That might not happen for another month before I make that association. You got it? So when I see your name, like, I don't know which class this is. Believe it or not, I got a web request, mostly from this class, for ad codes. And most of them started off the same way. Hello, Mr. Brown, can you please send me an ad code? And some of you are sitting here, you're probably laughing now. And I'm looking at, I actually have 8 classes because I have several online classes. I'd email back, which class? Can I just pick and choose one? So yeah, it's the same thing. Kind of identify, makes it easier on me. All right, I'm going to